So our next speaker is Ray Bradley. Ray is director of the Climate System Research Center at the University of Massachusetts Amherst and a university distinguished professor in the Department of Geosciences there. His interests are in climate variability and why climate changes over a large range of timescales. Ray is very famous for his work to reconstruct the temperature record over the past 1,000 years. And today he'll speak on Holocene Arctic climate variability, past, present, and future. Thanks, Ray.
Actually, this is a scrambled together talk at the last minute, but I thought it might be interesting to look at the issue of recent change, future change, and in the context of the past. So I'll start off with this statement from the various leading economies that they recognize the increase in global average temperature should be maintained or limited to no more than 2 degrees Celsius above pre-industrial levels. That was this meeting in 2009, and the European Commission and other economies have adopted this strategy to try to limit CO2 emissions to the point where global mean average temperature, globally average temperature, annual temperature, should not rise to more than 2 degrees C above pre-industrial level. And I want to just think about that issue with respect to the Arctic and with respect to the CO2 changes that we're envisioning or experiencing. So this is a reconstruction by Darrell Kaufman and others of Arctic temperature over the last 2,000 years. This is the whole Arctic, so including Siberia, North America, and so on. And what you see here are the interannual variations with some uncertainties associated with it. The red here is all we know from the instrumental period. So if we didn't have any paleoclimate reconstructions, this is all we would know about Arctic temperatures. And what we see here, and this, by the way, is with respect to the average for 1961 to 90. So these are deviations, positive or negative, with respect to that mean. And there are a couple of other earlier reconstructions, Overpeck et al. And here's the instrumental data, as I said. The dominant feature of this record, as you can see, is a slow decline followed by this sharp rise. This is in an earlier iteration, this was referred to as a hockey stick type of shape. The question is, what drove that long-term decline in temperature? I'm just looking at the very lowest frequency, and the answer is orbital forcing. That's related to so-called Milankovitch changes, and in particular the timing of the precession of the equinoxes, which defines the time at which the Earth is closest to the Sun. And if we go back to the early Holocene, 10,000 years ago, the Earth was closest to the Sun during the Northern Hemisphere summer. Today, we're closest to the Sun in early January. And what that early Holocene change as a result of precession led to is significantly more energy impinging on the atmosphere during the summer at high latitudes. And I'll show you that in this figure. What this attempts to show, I'll have to explain this a little bit. Here's the months of the year, and each panel shows the anomaly of energy, the surplus or the deficit of energy relative to today. So if the color is red, there was a lot more energy, and here's the scale at the bottom here in watts per square meter. This is 60 watts per square meter. And each panel shows the variation averaged around the globe from 10,000 years to the present, going from 90 degrees north to 90 degrees south. So if we go to July, for example, here, 90 degrees north, 90 degrees south, 10,000 years ago to the present, you can see that in the high latitudes, in the early Holocene, there was a lot more radiation being received over the Arctic region, and that declined through the Holocene. By contrast, let's just pick another month here. Let's say November here, there was less energy between the equator and 60 north, and that slightly increased over time. And the similar thing happened in the southern hemisphere. So you can see that every month is different, but during the summer months, particularly May, June, and July, in the early Holocene at high latitudes, there was a surplus of energy, and that declined through time. So that resulted in higher temperatures in the early Holocene, and if we take this regression line and we extend it back in time to 7,000 or 8,000 years ago, what we find is that temperatures were about 2 degrees Celsius warmer than the pre-industrial levels, which here I'm defining as, say, 1600 to 1800 AD. So as a result, purely of orbital forcing, the early Holocene was warmer than the pre-industrial level by about the amount that we're talking about for the post-industrial era, the limit that the industrialized nations are talking about for the future. And we're already warmer than that, of course, by about half a degree or so. So we're really talking about this early Holocene being about 1.6 degrees Celsius higher than the recent values. Now, we all have heard about Arctic amplification, and this is a figure from a paper that Giff Miller and Julie Brigham-Grady published. I don't believe this figure, by the way, but I put it up anyway. Nobody ever gets an R squared of 0.99. That's the first thing. As soon as I see that, I say, well, this can't be true. So, but anyway, the argument is that if you plot global temperature anomalies here, versus Arctic temperature anomalies, there is an amplification of about 3.4 times. So Arctic temperatures warm 3.5 times faster or greater than Northern Hemisphere temperatures. And these are various periods in the past: last glacial maximum, Holocene thermal maximum, little ice, last interglacial, and so on. So let's just accept that that's true for the time being, of an amplification of about 3.5. If we look at the model simulations, this is now latitude on this axis from 30 to 90 degrees north, and this is various IPCC models. Each line represents a different model, and it shows the polar amplification of mean annual temperature relative to the global mean for 2 times CO2. So what does that mean? It means that as we go to higher and higher latitudes here, the temperatures rise relative to the global average. So with 2 times global warming is here, 3 times the average of global warming is here. So you can see that as we get north of about, say, 70 degrees north, the amplification factor in the models is 2 to 3 times, which would support the idea Julie had for the longer time period. But this is mean annual temperature, mean annual temperature. We can look at another set of models, and what this shows is these Arctic climate impact assessment models, which were selected because they represent the Arctic particularly well. If we look at the global rise in temperature from 2000 to 2100 here, and compare that with the Arctic rise in temperature over the same interval, again, the Arctic seems to warm up about twice as fast as the global mean for this particular emission scenario. But again, this is mean annual temperature. If we look at this in a little more detail, now we look at, here's a bunch of different models. On each of these panels, we have latitude from 90 north to 90 south. We have months of the year from January to December. And what you see is most of these colors are temperature anomalies for 2 times CO2. what we see mostly is that it's not the summer months that are warming, it's the winter, the fall and the winter months. And if we focus in on the summer months, we see a quite different picture altogether. And I've just cut out from this picture all of the summer months. So now we're going from June to August at high latitude. So this is 90 north to, I think, 60 north. And what you see is that those colors, which we saw here, including going all the way up to 10 degrees C in red, are now all at the other end of the spectrum. And in fact, most of the summers in the Arctic in all of these different models are on the range of 0 to 1 degree Celsius. So the summer warming in the models is much, much less than the mean annual temperature anomalies that we expect. We look at a few more specifically, so we can look at the geography of this. This is the 4 seasons. Here's 2011 to 2030, going through to 2070 to 2090. And you can see clearly, if we look at the colors, that it's the Arctic here which is changing in the summer months very, very little. And it's simply because all that heat is being soaked up by the snow and the ice. And it's mostly in the autumn and the winter months where that warming is taking place. So now let's go back to that figure I showed earlier. Here's what we've seen over the last century or a millennium or so. Here's the pre-industrial levels. Here's the early Holocene. If warming from this point on was 3 times the global average, we'd be off the scale here. 2 times Celsius warmer would mean a warming in the Arctic of 6 or 7 degrees Celsius. But that would be a mean annual temperature. This reconstruction is summer temperature. So we've seen from those earlier models, earlier examples, that the warming in summer is likely to be much less, probably on the order of 2 degrees C, or 1 times the global average temperature, not 3 or 4 times the global average temperature. So that would place the expectation for later this century to be summer temperatures in the Arctic would be similar to the early Holocene values that we saw. So then the question is, can we look at the early Holocene as an analog for what might be in store for us? Here's a few examples from northern Siberia. The tree line migrated north. This is larch, this is birch. Maximum forest expansion was between 5 to 8,000 years BP. In fact, because the sea level was out here somewhere, so the tree line actually reached the northern coast of Siberia at that time. If we look at an ice core record from northern Ellesmere Island, this is Agassiz ice cap, 80 degrees north, 6,000 or 7,000 feet above sea level. You can see this is the melt that was taking place on the ice cap. In the early Holocene, that ice cap was melting away, just as we see parts of southern Greenland today. And recent warming here, this is the last 25 years, shows that we are now approaching melt values that were typical of the early Holocene at high latitudes in the Canadian Arctic. Several different records of sea surface temperatures in the Norwegian Sea, going from 10,000 years to the present. You can see all of these show a maximum of temperatures in the early Holocene, so there was a stronger North Atlantic drift. And in fact, up here, all the way up in Svalbard, there were blue mussels. The Mytilus edulis was common in the early Holocene. This disappeared over the last few millennia, and it's just started to reappear. The last time Mytilus edulis was found in Svalbard was during medieval time. And now it's just been found to be recolonizing. So we're starting to see the changes in this part of the world that were quite common in the early Holocene. Up on northern Ellesmere Island here we have ice shelves today. These limit the penetration of driftwood into the coast. And yet if we go back to the early Holocene, these are radiocarbon dates on driftwood from Phillips Inlet, which is over here, and Ward Hunt, which is over here. And you can see that driftwood was penetrating into those coastal areas in the early Holocene, and it was only in the late Holocene, the neoglacial, when these ice shelves formed, and it basically blocked off the coast from receiving driftwood into those fjords. And by the way, a remarkable find here on northern Ellesmere Island was a narwhal tusk, which dated 6,700 years ago. So there were narwhal that were inhabiting this coast. You would never see narwhal in this part of the world anymore. There's just too much ice. So presumably there was a lot less sea ice at that time. And finally, there were bowhead whales extensively in the inter-island channels in the early Holocene. We're starting to see bowheads in that area too today, but there were certainly both Pacific and Atlantic bowheads in this region in the early Holocene. So there was a lot less sea ice. So, and this is part one of my presentation, by the way. Don't get carried away. So here's the conclusions on that. Paleoclimate records in the Arctic reflect reflecting summer conditions, point to insulation forcing as the primary factor in long-term changes. Early Holocene summer temperatures were 2 degrees C above the pre-industrial level, and that's probably what we're going to see with 2 times CO2 in the summer months in the Arctic. Certainly the winter will be likely to be a lot warmer. And therefore the early Holocene might be a good analog of conditions that might prevail in the Arctic later this century. Now, what I would like to do, and this is just because Julie suggested it, since there's a lot of archaeologists here, I would like to just say very briefly another quite interesting story. This is a sediment record that tells us something about human occupancy of the Norwegian coast. This is up in the Lofoten Islands. This is a beautiful reconstructed Viking settlement at Borg. And we did some work, this is up here in northern Norway. We did some work right around the Viking settlement. This is a lake called Lilandsvatnet. The Viking Museum is over here. What we were interested in trying to determine is could we separate climatic and human impacts in the sedimentary record. So we took some cores from Lilandsvatnet. This was the Viking chieftain's domain, so to speak. There was a connection here to the sea, and he brought his Viking boats into this shallow lake. But there were also farms around Lilandsvatnet. We have very good radiocarbon control. I won't go into the details. We also have tephra that we were able to link to Icelandic eruptions, so we have extremely good chronology on this. Traditionally, measures of human influence on the environment use these kind of things. They look at magnetic susceptibility, which tells you something about soil erosion, landscape disturbance. Pollen, of course, is a crucial parameter for looking at vegetation changes resulting from human impact. Charcoal as a result of fire, often due to human activity. And then also, perhaps connected with all of this, changes in sedimentation rate, which might be related to anthropogenic activity. The problem with all of these is they could also be due to natural disturbance. This could be due to more rainfall, for example. The fire could be natural. The climate could change, and the pollen would vary, and so on. So it's difficult to separate human and climatic influences. This is a pollen diagram done by Voren from the area around the lake. I won't go into the details. Suffice it to say that if we look in detail, trees started to decline maybe 3,000 years ago, and grasses started to increase. That's really all you need to know from this pollen diagram. It was a change in the fundamental distribution from trees to grasses. Why? Was that due to human activity or not? What we did, and when I say we, of course I don't mean me, because I wouldn't even know how to turn these machines on, but my student, Rob Danjou, looked at these various biomarker proxies, and I'll just mention what these are. These are sterols, coprostanol, campestanol, which are related to human shit and animal shit, basically, poop. And what happens is, in the digestive system of animals and people, this material is produced. It gets passed through onto the landscape, when people poop on the landscape, and then it gets washed into the lakes, as you'll see in a minute. We also looked at polyaromatic hydrocarbons, which are formed during the combustion of organic material, and these various alkanes, the different carbon chain lengths, which relate to either trees or grasses. So these are the various proxies we use to try to identify the human footprint, so to speak, on the landscape. So here's the record, the 7,000-year record. Coprostanol is produced by humans, almost exclusively. Actually, humans and pigs produce coprostanol. But what you see in this record from 7,000 years ago to the present, no coprostanol at all. And then suddenly, around, I think it was 2,500 years or so ago, suddenly coprostanol appears in the landscape, in the sediment. So people arrived in this area and started pooping, as they would. Not that there's a connection between arrival and pooping, but it could be. If we look at stigmastanol, this is produced by grazing animals, cattle and other herbivores. You can see that it's not zero from 7,000 years ago, but it's pretty flat. And this reflects the presence of deer and moose in this area. But you also see at the same time it suddenly increased very dramatically when people arrived in the landscape. So here's the total of these two over time. Notice also these polyaromatic hydrocarbons. This is an index of biomass burning. Nothing going on, or very little, perhaps some natural fires above the zero here. And then as people arrived, it goes up and up, as you might expect. They come in, they start burning the trees to provide grazing areas. And here's the carbon chain length index. These higher numbers represent trees, and you can see the tree vegetation declines, especially after people arrive towards the present. So now it's predominantly a grassland, shrubby kind of environment. Now let's just blow up the latter part of this. So ignoring the pre-occupancy period, now look at the variations that have occurred over the last 2,500 years. And if we look at coprostanol and stigmastanol, these are the poop indicators. Look at the totals here. We can see that it reaches a maximum around about 450 AD, changing the time scale here to BC AD, 450 AD, suggesting that this was the time of maximum poop production, maximum occupancy, presumably. Then there was a period which in this part of the world is known as the Merovingian Depression. This was a migration related to social and political upheaval in the area, and the population declined over that period. And as one might expect, so did the poop in the landscape. Later on, there was the Black Death. I think 80% of the farms in this area were abandoned at that time. And then we we move into the Little Ice Age period here, which interestingly has the highest burning signal. So presumably those people who were living here burned a lot of peat and other biomass simply to keep warm. And we also reached the minimum tree index in the landscape too. Now my question when I looked at this was, why are these variations, what are these ups and downs really related to? We can perhaps ascribe some of this to socioeconomic factors, political factors, perhaps to singular events like the Black Death. But what we found was a long-term summer temperature reconstruction, which is shown here in blue based on tree rings from this area. And I've superimposed that here on the coprostanol record. We had to adjust this by an 80-year lag, but that's well within the dating uncertainty of this record. But you can see there's a remarkable fit here between the fluctuations of summer temperature and the record of coprostanol. Of course, we can't link the coprostanol entering the sediment to the population. But the suggestion here is that the human population was closely linked, closely affected by the fluctuations in summer temperature. And remember, we're up at about 68 degrees north here. We're really at the limit of farming. Barley farming was practiced here, but it was really at the growing degree day limit. So a small change in summer temperature here probably had quite a big impact on their abilities to survive. So, biomarkers from human and animal feces can provide definitive evidence of human activity in the region. When there are no people, you will not find coprostanol in the sediment. Human activity can be traced through biomass burning and vegetation composition. In this part of the world, population expanded and human impact on the landscape began around 2250 BP. That's when farmers migrated from the southern part of Norway along the coast and began to settle in the Lofoten Islands. Population was strongly influenced by changes in summer temperature as well as by societal factors. And I think fecal biomarkers offer a unique opportunity to identify and trace the presence of people in the landscape. And I think this new technique could be used in many other archaeological settings. I've suggested in a recent proposal to try this in the Faroe Islands, for example. I think it could also be applied in places like Rapa Nui, Easter Island, and other places where there's still some controversy about when people actually first arrived in an area. And I'll stop there.